We have a super exciting session for you today. This is a deep dive into a preview of what you saw in Jensen's keynote yesterday, an introduction to building humanoid robots. We have an incredible lineup of speakers today. Jim Fan, Yuka, Leela, and Yen. We have Jim and Yuka are from our NVIDIA Gear Research Lab. Yen is a leader on our engineering team, and Leela is also a leader on our engineering team. So I'll hand it over to Jim.
All right. So it's 8 a.m. and we have a full room of developers. 8 a.m. is not for developers. I think we should host these sessions at 1 a.m. instead, where that is our peak productivity of vibe coding. So next time, Groot Hackathon, 1 a.m. All right, so I think we are a very interesting generation. All of us here were born too late to explore the Earth and a bit too early to travel to other galaxies. But I think we're just in time to see robotics solved. And NVIDIA is a company built for a generation as great as ours. So of course, we're going to tackle one of the most challenging problems in AI and perhaps in all of technology, which is robotics. So today, we're going to start with 3 statistics that motivates Project Groot, 3 computers that define Project Groot, and 3 research principles that implements Groot. So are you ready for some math? The first number, 4.2x. This is the increase in job vacancies in the 30 most advanced economies in the world over the last decade. And here, this line is trouble. Because anything above this line means that even if every able-bodied human being is employed in these countries, there are still not enough humans to do the job. And these are the top vacancies by sectors. And it's from a report by McKinsey Global Institute. So what do you see in these sectors? Let me highlight a few in red. What do they have in common? The thing that they have in common is none of them can be solved by ChatGPT, because you need a physical body, right? Leisure, hospitality, healthcare, construction, transportation, autonomous driving, right? Manufacturing, all of these require physical work. And these are the top job vacancies. And the second number is $1.4 trillion. And this number represents the gap in economy that you can bridge if all of these jobs are filled. And that is 1.5% GDP gain of the entire US. And just to put this number in perspective, 1.4 trillion is the GDP of the entire country of Spain or Mexico. So basically, the world is losing $1.4 trillion every year because there aren't enough human beings to fill the job needs. And the third number is a much smaller number, $40K. So the world has been building humanoid robots for a very long time, like 30 or 40 years ago. In fact, in 2001, NASA built Robonaut that requires 1.5 million at that time. And counting inflation, this is probably like 2 million or even more. And then we see the cost of humanoid just exponentially decrease. So there's this general pattern that any mature product, the price will tend towards its manufacturing cost. And for humanoids, they only take 4% of the metal of a regular car. So the 40K is just today, and it's roughly comparable to a car. But in the future, it's going to go down much more as humanoid robots start to ramp up production. And this is where it's going. Now, that's a scene from last year's GTC. And we can see that there are 10 humanoids on stage. 9 of them mechanical, and 1 of them biological in the middle. Jensen, right? The biological humanoid in this picture is still the smartest. But maybe someday, that won't be true anymore. And let me take you all to NVIDIA Gear Lab. So this is the lab that we research and build humanoid robots. So that's me and Yuka here in this picture. Basically, at one point, we had 4 different humanoid robot species. And at that time, it's probably the most diverse number of humanoid species per square feet on Earth. during that time. Next, let's talk about what does it take to build Groot, right? What is Groot? So to build robotics, first we need to either collect or generate a lot of synthetic data. And then once you have a huge data set, you will feed it to train foundation models, which become the brains for humanoid robots. And after you train these models, you want to deploy it on board so the robot can be autonomous. And this is what we call the physical AI lifecycle: generating data, consuming data, and then deploying the model. And correspondingly, NVIDIA has defined this three-computer problem that starts with the OVX computer, which is a simulation computer that generates tokens, be it using teleoperation with XR devices or simulation suites like Isaac Lab that's GPU accelerated. And once you generate these tokens, the DGX computers will learn from the tokens. It will compress trillions of tokens into this artifact. And this time, it was already announced yesterday, called Groot N1 foundation model. And finally, you got to deploy it. You want to deploy it on a low-cost, high-efficiency, low-energy consumption edge computing device, and that is the AGX computer. And these computers are for deploying tokens. And all of these combined defines Groot. So Groot is not just a single model. It's not even a single product. Groot is a strategy. It's a strategy to build robotics, a strategy for NVIDIA's future physical AI computing platforms. And next, I will hand the mic to Yuke to talk about how we implement Groot.
All right, so now you hear the high-level vision of Groot. Like I will talk about like the research principles that underlying our efforts in building Groot. Overall, I think there's three research principles that really kind of guide us, like day-to-day development of the Groot model. The first is called Generalist. We want to build a Generalist model first, and then using this Generalist as a backbone to specialize it and to turn into a better specialist in different domains and different downstream tasks. And the second is called a dual system. That's our vision to build the autonomy stack, right? So if you look at robotics, how the kind of a different architecture, how the models evolves over the decades of robotic research, it starts with a highly modular stage pipeline, right? So people first focus on solving perception and then planning and decision making and control as a completely separate problem, and then they piece them together after solving this individual subproblem. But the challenge of that is it creates a kind of information bottlenecks, so you cannot really do full stack optimization across different modules. And then deep learning comes in that people have been looking into training a monolithic model to do direct pixel to torque. But the challenge of that is you lose that kind of nice property of modularity and compositionality, right? So what we are really looking at is how do we have that kind of a compositional structures in the model, but we piece them together still that allows full stack optimization. And the last is what we call data pyramid. So one thing is different in robotics than large language model or vision language model is that there's no internet of humanoid control, right? So we cannot download robot actions from the internet and directly train into a model the same way as LLMs. So we need to be a bit creative in finding the data sources. So just want to kind of give more context on the three principles, right? So if you look at the development of neighboring field of AI, such as natural language processing and computer vision, I think that it shows a recurrent pattern of innovation. That it starts with some kind of specialist systems, NLP researchers, they spend years of research building some customized modules for sentiment analysis, semantic parsing, information extraction, or text summarization. What all those kind of language models like ChatGPT, Llama, and Cloud and have shown is that now we can actually consolidate training into one to build one big general purpose model, right? And these models are trained on massive amount of tags on open-ended objectives. As a result, they have a general understanding of word knowledge and human language. And as a result, we can actually use this generalist model to adapt them for a variety of language applications. You can let it to write poems or like haiku is much better than I do. It can auto complete your source code. Our researchers and the engineers use it all the time, and it can give you like the travel plannings for the next trip or vacation, right? So if you think about like, so if we do any of this NLP application from scratch, it's incredibly hard. But by building this generalist model first, it allows us to build better specialists. Now that let's turn our eyes into robotics, right? So the status of robotics is similar that we have researchers that build amazing specialist applications of robotics, so they can like solve a Rubik's Cube using a dexterous hand, and you can traverse uneven terrains with a robot dog. But we're still far from the dream of having a general purpose robot that can be deployed to homes or factories to perform every kind of human task that we'd like to do in human environment. And you see that I call that a generalist specialist generalist. By that I mean that they should not be generalists for generalist sake, right? They should not be jack of all trades, master of none. Instead, they should have a set of core competencies, but also they should always be learning and adapting to new scenarios and to develop a deep expertise in the kind of target domains where they deploy. So on our way towards this specialized generalist, I argue that we need to build this generalist robot model that motivates like the Groot N1 effort. We're going to talk soon about like the foundation model efforts that we have been doing here at the Gear Lab. So a lot of our goals align with the mission of building a generalist robot model. I think this is really a fascinating research topic, but also as a huge technical undertaking, right? So, and we're not building our robots here at NVIDIA, but like, so we really want to build a core tech and not only just foundation model as a single artifact, but also all the toolings and infrastructures and the computing platforms to activate the entire ecosystem, right? So to engage our industry partners to solve this grand challenge together. Jim already mentioned a bit like so why humanoids, and I want to just make a little bit more technical points. One is, well, if our goal is to build a generalist robot, right? We need a general purpose, versatile body, right? So because that we are talking about physical agents, so their physical embodiment largely determines their capability envelope, right? If we want to work on robot dog, at best you get dog level intelligence, which is pretty cool, right? So I think like so none of the robot can do the kind of agility of my dog can do. But still, if you want to deploy robots to perform everyday tasks in human environments, we need a human-like body. The second is, Jim already mentioned the number 40K, right? So, and we see dramatic decrease in the robotic costs, and they're not only just cheap, but also very capable robots. Just to show an example, this is one work that from the Gear Lab recently called ASAP, where we use Isaac platform to do large-scale reinforcement learning training to allow us to generate like very agile dynamic motions with this robot. The third is we call humanoid robotics a brownfield project because that we human build the world for our human form factors, right? So in principle, if we can have the robots that share the similar physics, we can just roll in the robots into the human world without tearing down all the houses and the factories and build new ones from scratch, right? So it doesn't make economic sense. So ideally, if we have robots that like look and behave similar to us, like so they can reuse a lot of like, real world infrastructure, and they can use all the tools and the equipments that we built for human body. And the last is what actually I care the most is a data argument. I mentioned that like, there's no internet of robotic control, right? So, but because of the similar physics of a humanoid robot, and there's actually tons of human-centered data sitting around on the internet, right? So from like all the motion capture databases from Hollywood, from the entertainment industry, all the way to YouTube videos and all the internet videos of showing humans doing all kinds of interesting things, like loading dishwashers or like on some IKEA furniture, right? So maybe the similar embodiment of humanoids will make it easier for us to tap into this kind of human-centered data source. That's one of our key hypotheses. So now that I kind of motivated humanoids, and a lot of our designs and follow this high-level principle that's inspired by recent discovery in human cognition. Like, how many of you have read this book, like so Thinking Fast and Slow? I think it's already, the idea is already popularized. I see maybe half of you raise a hand, right? So you can think, well, like, so it's characterizing these two thinking systems in human brain. Like there's a fast system called system 1. It's a unconscious, intuitive, and reactive. In robotics, you can think about, well, you need to build robots to react quickly to all the kind of like surroundings with some kind of closed loop control in the here and now. And then on the left, it shows like a system 2. Right? So that's a slow brain. That's conscious, deliberate effort for thinking. So in robotics, and we kind of need the high-level cognition, reasoning, planning in order to decide, like, so reason about the surroundings and the task objective and to decide what to do. So a lot of our research and the Groot N1 foundation model building goes into thinking about how to integrate this two thinking system into a coherent learning framework. And with that, I'm going to hand over back to Jim to talk about the details of the N1 architecture.
All right, thank you so much, Yuko. So let's pretend to be a neurosurgeon, and you have a brain in the vat. And unlike brains such as LLMs, right, ChatGPT that lives on the cloud, this brain actually runs on hardware. It's got read-write access to the physical world. And that is Groot N1, the world's first open humanoid foundation model. And let me take a tour with all of you through this neural net. So on a very, very high level, Groot N1 takes two types of tokens and generates one other type of token. So if you recall yesterday at Jensen's keynote, the opening sequence is all about token. And N1 is no different. It's just got more interesting tokens. So you have the visual tokens going in, which is the egocentric view of the robot from its camera, from its eyes. And you have language instructions, just regularly tokenized, like any LLM. And you output these motor action tokens. And that's, on a high level, the input and output. But what exactly does Groot N1 see? This is what Groot N1 see. So you give it an instruction, and then it starts from a scene, like this. So the task is to pick up these industrial objects and then put them neatly in this yellow bin. And this is what Groot N1 outputs. Basically, a sequence of motor actions that controls the robot arms and hands and actually complete the task. But this is only for us to consume. The model doesn't actually output this. The model outputs this. These are the actual outputs, right? A set of continuous values, a bunch of floating numbers for each motor, and then these motors will complete a task. So from the model perspective, it's these really weird continuous curves. And the model needs to learn how to output these curves. So how to do that? We have two very powerful tools that have been shown to work over and over again in multimodal domains. The first tool is LLM, right? They generate discrete values like text, symbols. So on the high level, it's a transformer model that takes a sequence of integers and outputs another sequence of integers. So they're discrete. And these discrete sequential models are great for reasoning. And then there's another very successful model family called diffusion. And they're most seen in generating images, right, like Stable Diffusion, or generating videos like Sora. So what diffusion is very good at is they generate continuous values, like pixels and audio waves. And diffusion works in parallel, right? You don't generate one pixel at a time. You generate the whole image in parallel, like a GPU, right, like a rendering engine. So how do we combine these two to solve Groot? On the system 2 that Yuka mentioned, we have this vision language model that uses these discrete style tokens and autoregressive models to do vision language reasoning, to understand the scene and instructions. And then the actions just look like an image to us, right? It looks like an image, like an audio wave, like any continuous vectors. So we encode the robot states and then put noisy action tokens into a diffusion, and then we take a bunch of diffusion steps, and that becomes the actual motor action output. And the diffusion transformer is system 1. It runs at 120 hertz, which is required. It has to be very fast for the robot to be reactive. Otherwise, it's going to have very kind of non-smooth and jerky motions. And what's more, N1 is an open humanoid foundation model, but we just decided to give it a bit more feature to make it cross-embodiment. So Groot N1 was actually trained on very diverse embodiments, ranging from a single robot arm with gripper to 2 arms with hands, 2 arms with gripper, different types of robot arms, you name it. We have a collection of embodiments, and it's cross-embodiment. So how do we implement this? Let's again look at system 1, right? That's the same diagram, but it's just a little bit more dissected. You basically have robot states going through a state encoder, become some tokens, and you have actions going through the action encoder, become some tokens. And through these alternating layers of cross and self-attention, it finally gets the actual actions. And we just add one simple concept here to make it work more than just humanoid robots. So it can also work on industrial robot arms, and you name it. And these green ones are the embodiment-specific adapters. Basically, for every different embodiment, you have a different set of adapters, but you share all the intermediate layers, which are interesting representations that the neural network has learned across lots and lots of data. And then you simply feed the vision language model into it. So we use the Eagle 2 VOM, which is part of NVIDIA's larger VOM family. Now let's see Groot N1 in action. So we put N1 in a kitchen setting, and then it's able to place very different objects, unseen objects, new geometries, is able to grasp and put it on the plate. And the robot can also be romantic, right? We have done some interesting tasks here. You give it some flowers, it's gonna pass you the champagne. Yeah, this is a successful shot, but during development, we had, yeah, you can picture that. You can picture that. It was a mess. It was a mess. Yeah, but this is a clean shot. Yeah, that's when the model converges. You know, it becomes romantic. And then Jensen showcased this very interesting task of an industrial task that requires 2 robot coordination. Basically, the left robot, right, takes some machinery parts and pass it to the robot on the right, and then the robot on the right will look at this and take this out, and then pour the machinery parts into the yellow bin. And this is just one sequence. You can do a lot more than that. Great. And even for humanoid, right, we also can have different types of humanoid. So we have an ongoing collaboration with 1X, the Norwegian company, humanoid company, and this is the 1X Neo Gamma, their latest version. And we fine-tuned Groot N1 to perform these household tasks. And this is fully autonomous, no teleoperation, fully autonomous from photon to action. And if we look at some quantitative results, we compare Groot N1. It's a 2 billion model, only 2 billion, right? It's a very small model that punches above its weights. And you don't want a 300 billion model because it's not going to fit on the edge computing device. That's a constraint for physical AI. And finally, just as one more bonus, we also fine-tuned Groot N1 on the $110 Hugging Face Le Robot SO100. So this is an open source hardware from Hugging Face, very cheap, affordable. So I think everyone here can get started today. And you can fine-tune Groot N1 and look at this cute robot go. Yeah, so basically, open robot brain running on open hardware. Sounds just right to me. All right, gonna pass the mic back to Yuke to talk about our training strategies.
All right, so GMCLA is a 2 billion parameter model, and we designed the size to fit in our edge GPU, but still 2 billion parameter is actually a pretty big model, right? So the common wisdom in machine learning is if you have 2 billion number of parameters, you probably need 2 billion data points in order to train them. So the model is powerful, expressive, but also data hungry, right? So how do we solve the data hunger problem, like to train robotics? Well, this is a concept that I kind of introduced about 2 years ago called data pyramids. So back then, the we were just a little bit desperate because we just don't have that large data set in order to train this computing parameter model. So we took a very pragmatic approach, saying that, well, let's just see what's the data sitting around us, right? So, and then I can organize them by volume or by size and into this kind of pyramid shape. The first on the top is real world data. So these are the things that well, you can tally up to collect. They are expensive and only small scale because robot like humans only have 24 hours a day, right? So that's how much data you can collect. And at the bottom, you have web data. So these are things like YouTube videos, Wikipedia pages, Reddit posts, right? So they're very unstructured, multi-model, but they're very human-centered, right? So in principle, that we can extract a lot of knowledge from that. And in fact, I think so in Europe last year, Ilya Sutskever make a point saying that web data is the fossil fuel of AI. But still, the human world, human society collectively generates exabytes of data per day, right? So that's kind of that exabytes of digital oils are coming in the field every day. So that's still a lot, and exabytes means millions of terabytes. And then at the center, between real robot data and web data is synthetic data. So these are the things that that's coming from the physics engine, graphics renderers, so that NVIDIA here would build a lot of tools in-house. So you might argue that in principle, we should just let the GPU run, and then we can get infinite amount of synthetic data. But in reality, the challenge to use synthetic data is that you need a really good simulator, you need good assets, and then right now, there's still a human in the loop, right? So you need a human, practitioners and graphics designers and to create all the assets and orchestrate the simulation environments in order to make best use of that. Otherwise, there's always some kind of a sim to reality gap, that hinder the utility of these models, of this data. So, well, given that kind of a complementary strength of these different data sources, we're just telling ourselves, well, let's not just pick favorite, right? So why don't we find ways to leverage the entire data pyramid? So a lot of our research and in GR looks into what's the best strategy to leverage the entire pyramid for learning. I think for the bottom of the pyramid, we already have a good idea. That is the recent advancements in vision language model. These models are super powerful in consuming large scale of internet scale text and images, and then reason them jointly together. We have seen what I call a Cambrian explosion of this vision language models and from the community, as well as here at NVIDIA, we have been building new ones, including the long Leela work and also the Eagle VLM work that we use for the Groot N1, that we try to extend the context lens of these models for video understanding. For the top of the pyramid, usually this real robot data are collected with teleoperation. That means that so you have a human using some kind of input devices to remotely control the robots to perform a task, and then you can record the data, record the trajectories. So in the video that I just showed you before, the video did not play, and it was a Apple Vision Pro system where we show that we can actually use the online SLAM capability of Apple Vision Pro to track the human hand in 3D, and we can transform and map that to the robotic hands and to collect data. Well, let me see if this video can play. Oh, can we come back to the previous video, please? Previous slides. Okay, so I found the button here. So it remains unclear, so how much data do we need to train our robotic foundation model? I think fundamentally there's a limit to such a real robot data collection because we only have 24 hours of wall clock time, right? So the data really grows only linearly with respect to the time and money and the human effort we put in. And this picture shows if we were to scale this approach for large-scale real robot data collection, typically we build robot farm, right? You have just a parallel, have a bunch of robots collect data 24/7. So at NVIDIA, I think we take a simulation first approach. That means that we're not just putting our bets on scaling up real world data, the top of the pyramid only, but rather that our hypothesis is that we look into synthetic data and simulation data as an effective way to augment real-world data sets, right? And the nice thing about synthetic data is that once the simulation is built, so you can vary different axes or different factors and to exponentially generate many data points. And this is showing one example running in NVIDIA Omniverse that you see that through procedure generation, we can vary different conditions, and then going from one trajectory, we can multiply them, so to generate many different variations and to significantly augment the data sets. Or if you imagine training on this augmented data sets will facilitate the generalization of the model. Well, this is quite cool, right? So if simulation is useful, why this has not been widely adopted yet? Right, so I mentioned the challenge briefly is the human in the loop, right? So right now there's still a high human cost involved in leveraging this synthetic data because there's a graphics designer and programmer needs to build a simulation. What really changed the equation, so that really excites us, allows us to look deeper into this approach, is this availability of generative AI models, right? So now that we have much better models that was able to kind of generate the 3D assets from a language prompt, we can use large language models to generate the reward function and task goals. We can use image generation models to randomize the textures and the lighting conditions, right? So that kind of automatically gives us a large variety of realistic things without kind of a human kind of a curation. And this is showing one example from one of our research work demonstrating how do we leverage a collection of generative AI tools and to create this kind of large-scale realistic kitchen environment. Once we have the simulation, we also need a behavior data, as in we need trajectories to feed into the Groot training. So one of the recent work we did is called Dex Mimicgen. That essentially, you can think about it as some kind of trajectory multiplier, meaning that we just collect a handful of demonstrations, and this is using the Apple Vision Pro system that I talked about earlier. We collect a handful of demonstrations, say 5 demonstrations, and that can be done in 10 minutes time. And then we just let the compute do the work, right? So we run simulations and repeatedly in different conditions and try to synthesize new trajectories in different conditions. And so we just let the GPUs and do the work, and we kind of treat the engineer time for compute resources. So let me use this example to demonstrate, the high-level idea of this data generation pipeline. See that if you want to grasp a mug with a robotic gripper, right? So and then oops, let me go back. So, and on the left is a source trajectory that you pick the mug with a gripper. On the right, you show that you instantiate the mug in a different location, and then we can actually transform the trajectories and to the locations to pick up the mug, right? So in the new initialization conditions. So if you compare left and right, so there's something doesn't change. That is the relative pose between the robotic hand and the object, right? So in kind of mathematics, and you can think about this, some kind of functional equivariance, if you want to be nerdy here. That means that as we are preserving the relative pose of the robotic end effector and the object under some SE3 transforms. So that's essentially the underlying idea of how we do data generation. But in order to apply this to humanoid robots, and there's an additional challenge we need to tackle because the humanoids needs to kind of have 2 hands and they need to coordinate with each other. There's 3 different types of behaviors. Sometimes these 2 hands are doing things independently. Sometimes they need to kind of work collectively to solve a task together. Sometimes you need to complete one task and with one hand before you can kind of start doing the next task with the second hand. So in this system, we actually build logic to automatically identify these different modes of operation and then build some state machine logic to transit from one state to another. And we show that by leveraging this synthetic data, we get good scaling properties, right? So going from 50 demonstrations, we can just let the GPU do the work and generate a 3,000 demonstrations that we train the models as a different size of the data sets. And we show that so as we go from 50 to 3,000 automatically generated trajectories, for free, no human time involved, and it improved the policy performance by 65%. Okay, so that's quite promising that we talk about the generative AI models to create the generative simulation. I talk about so this automatic data generation system to create the trajectories and behaviors. Why do we combine them together? So this is some illustration of the training soup we use for Groot N1, right? So you see that actually for the first and the third column, so they are teleoperation data that we collect in the real world. We got only like a small size of it. And then, so the second and fourth columns, these are the simulation data we generate in Omniverse and Isaac, right? And if you really squint, maybe you cannot really tell much of a difference, but like, of course, like there are some artifacts that you can tell that this is like some of them are simulation, but you get the idea, right? So as like so we get a diverse set of like simulation data that it start to cover a wider range of distribution, wider range of space, so that they can significantly augment so the small number of real data. So that's essentially the strategy that we use to leverage both simulation, synthetic data, and real-world data for training. That we start with some kind of human demonstrations that we collect in the real world, and leveraging that kind of a human demonstration or the real-world task as a source of inspiration, that we create some kind of simulation environment using generative AI techniques. And the specific simulation that we generate is called digital cousin. So digital cousin means that it's not a digital twin, right? So you might more familiar with the concept of a digital twin as like it's a one-to-one copy between the physical and the virtual instantiations. But cousin means that, well, you look like your cousin, but not exactly the same, right? So we are kind of treating some precision and fidelity for diversity and quantity, right? So by relaxing the assumptions that we can generate a lot more cousins than not necessarily like a banging head on to build an exact twin. So that allows us to generate orders of magnitude more synthetic data than the real world, right? So in the Groot N1 paper, we use like 100 times more synthetic data than the real world data. Now we have these two mixed data sources, and they're a little bit unbalanced. One is much bigger than the other, right? So to capitalize on this data, we need to kind of find some smart strategy. The idea is actually pretty simple. We just find some way, like sophisticated like so data mixing strategy just to combine these two together. We have some smart sampling to grab data samples from each of the data sources, but we need to make sure that we need to rebalance them because that there's a skewed data distribution, right? Because the simulation data is much bigger than real. And by combining this and co-train between sim and real, we show that so we indeed can benefit a lot from the synthetic data we generate, and then that like improve the robustness of the trained policy across like the many different embodiments from humanoids to robot arms. That's one way to leverage synthetic data. The second way that's based on the traditional physics engine and graphics renderer. And now that we're quite excited about the new development, a new type of neural simulation or neural renderers, right? So that's video generation model. Like OpenAI Thor, you have seen that I can really generate like a high quality, high fidelity videos. That we've been also looking into how do we leverage this type of video data for learning. So one of the ideas is like both the human videos and also the kind of neural generated videos from like a Sora-like video generation model, they don't really have actions, right? So that has been the challenge. Like if we don't have actions, how would you leverage them to train the same way as the teleoperation data sets? So we have to find ways to recover the action information from the action list data sources. So we have been developing techniques to learn some kind of latent action code books so that essentially that you can learn some kind of latent action representation that align across all different embodiments. So these are just two examples showing that like across like so many different robot arms, like human hands and the robotic humanoid robots, you can learn that kind of like a unified action space to align them together. And the concrete details can be found in our white paper. And then leveraging these techniques, right? So we can also apply this latent actions to neural trajectories. And by that, I mean all these videos are not real recordings from the lab, right? So all these videos are generated by a video generation model. What we do essentially is we provide an initial frame that is a picture that we took in our actual workspace. And we just let the neural video generation model dream what's going to happen, right, giving some language prompt. That allows us to generate the video sequences, and then we leverage its latent action representation to annotate the latent actions to this video. Now that with the annotated actions, we have the data set we want to use, right? So we have the observation action pairs that we can leverage as a robotic data, as like a standard robotic data set to train our model. So Jim mentioned so the Groot and One have cross-embodiment support. That's essentially what we are doing by treating these neural videos as another embodiment and to train the model together alongside with the real robot data sets. Okay, so that's kind of our data strategy. One thing that I would say that I talk about a lot of our research, that's in the form of papers, but a lot of the research really served the goal to pave the way for building real-world products. And many of the work that we did actually, we worked closely with the engineering team and to transfer them into the Isaac and the Omniverse ecosystem and share with the entire community for all of you to build the full-stack AI applications for robotics and in your target domain. And also, we work with partners in the ecosystem together to continue to develop and deploy our foundation models in actual use cases. So Jim already mentioned that one thing we really like is to keep things in the open. This is humanoid robotics is such a massive holy grail challenge in robotics that by no means that we can really solve it alone, right? So and then we are open sourcing this foundation model Groot N1 alongside some training data, evaluation protocols, and benchmarkings, and you can go to the GitHub and then copy the code base and then quickly post-train, fine-tune the models and see. I would love to hear your feedback and see what kind of amazing things you do with Groot N1. Okay. So with that, and that kind of concludes the research component of this session. I'm going to switch gear and hand over to my dear colleague, Yan, and she's going to talk about the engineering front of the Groot initiative. Yeah.
Thank you, Leela and Jim, for the awesome presentation. Hello, everyone. So I'll share the engineering side of the Groot. So as Jim mentioned, Groot is a strategy of NVIDIA, and it has 4 pillars. The foundation models, like the Groot N1, and also the synthetic data generation pipelines, and the simulators, including the Isaac Lab, Isaac Sim, built on top of Omniverse, and also the robotics computer on the edge, like Thor. And so physical AI is boring simulation, as Yuka and Jim just mentioned. And so with Omniverse and Cosmos from NVIDIA, you actually combine the both good side of them. So with Omniverse, you can build your digital twins or digital cousins, like Yuka said, in the digital world. And also you have the robotics gyms for you to do the training or testing for your robots. And then with that, you can also use Cosmos, which is a world model from NVIDIA, to convert those data or environments into photorealistic videos, and you can use that for your evaluation, for your training, to close loop and also close gap between the same to real. So for the simulation and robot learning frameworks, you have the access to the NVIDIA Omniverse platform of the SDKs and also the APIs. And with that, you can bring your open USDs, and also you have the physics engine RTX rendering. And built on top of that, there are 2 frameworks. The Isaac Lab, you can use that for robot learning. And it has a training, APIs, frameworks. You can do both of the imitation learning and also reinforced learning for it. And also we provide the assets and environments such as actuators, controllers, you name it. And so with that, we can actually doing a lot of things with robot training and robot testing. And for Isaac Sim, then you can also do a lot more. So Isaac Sim give you the capability with bringing the different data, and then you can import that into the format for the Isaac Sim. And also you have the sensors, utilities, and synthetic data generation pipelines, and also the interface available to you. And so next, let's dive deeper into some of the available workflows that we open source for you to try the ecosystem of NVIDIA. And so firstly, the Isaac group for the synthetic motion generation. This is built on top of series of research, including the DEX Mimic Gen that Yuke just mentioned. So firstly, you have tens of demonstrations from the human teleoperation. And here, one thing to note is that you don't necessarily need to have the physical humanoid to do that. You can actually give the teleoperation demonstration through the digital twin of your robots in the Omniverse, in the Isaac Lab directly. And we also provide the Groot teleoperation workflow for you to easily do that. And then go through the Groot Mimic. You generate hundreds of more synthetic motion generation, which is augmentation from the original trajectories. And then with Cosmos, you got like millions X of the training data with photorealistic renderings. And so next, I will also share with you a few workflows that enable you to build the whole mobility or even local manipulation for the humanoid. And so we open source the mobility and control workflows. As Yuke and Jim mentioned, we have principle of the System 2 and System 1. And for System 2 here, you have the Remember workflow, which we combine the vision language model, large language model, and vector database to enable robots to have long memory, like hours or days of memory, to directly interact with people. So you can ask it, where can I find the elevators? Where did you see a cat passing by? And then they will give you the goal and also answer your questions. And with that, we send that to the System 1. And again, this can all be trained together, or you can take each component for your use case as well. And then those goal positions go into the mobility workflow for training the foundation model, and that is also an end-to-end pixel, photo in, and action out. So with that, you got like the foundation models of the mobility with mobility policy and word modeling. And then that can send to the even higher frequency of the controller or whatever controller you want to use for your robots. And this is also cross-embodiment. We will dive deeper into that later on. And you might ask, how do I get tons of data for training those models? So we provide you the mobility gen pipeline where you have the capability and also all the code available for you to combine the Isaac Sim and also use Cosmos for the data augmentation on top of Omniverse. And then with those data, you can do the imitation learning plus reinforced learning in the Isaac Lab to guide those mobility foundation models that fit your use case. And then we can test those models in the virtual world in Isaac Sim or Mega, and also deploy that to the real robots as well. So for the mobility gen pipeline, you can bring any of your USD things in terms of scenarios, and also you can bring your own robot asset, basically your digital twin of your robots and digital cousin of the environment you want to deploy. And it goes through two steps, the mobility gen recording and then the replay and rendering. So with those two steps, you actually can have a lot of flexibility. So you can add additional sensors to wherever you want in your robot asset, and it will re-render for you without even need to rerun the recording states. And regarding the action of the robots, you have the multiple ways of the control methods. You can use the teleoperation in the digital world. You can also bring your autonomous stack to this. We have the API for you to try them out. And also we provide random action and also the built-in default planning stack as well for you for your convenience as well. And then with those output of the recorded data, you can feed that into the NVIDIA Cosmos, the transfer model, and get the augmented data for it. And those data and also original recording data can be used for model training and algorithm testings. Okay, so these are few examples that we saw, like the coming from the mobility gen pipeline. And looks like on the left, the video didn't play, but actually a box drop down from the warehouse, and also we show that it navigates through easily. And on the right, you can also see we have the open source visualization tool for you to introspect the data set as well. And as we said, so you combine the Omniverse and Cosmos, you get beauty from both sides. So from the trajectory recording, and then the replay rendering, and then you got the videos, and with the Cosmos transfers. And so from the video we just saw, actually with the Cosmos transfer, you got very photorealistic. For example, you can see from the right side, you actually see the things on the ground, and you can give any prompt to it. For example, you can change the color of the shelf, you can change the environment, you can even put some water on the floor to test your robot's robustness as well. And so next, we will also share with you 2 workflows that for you to build your robust cross-embodiment mobility. And those things can also combine with N1 so that your robots have both the manipulation and mobility capability together. And so firstly, in this pair diagram, we start with the X mobility, which is imitation learning based workflow. And again, as we said, all the data coming from the Isaac same digital twins. And X mobility is end-to-end generalizable navigation with the word modeling. And then after that, you get a pre-trained policy. Then we feed that into the campus workflow, which is cross-embodiment mobility policy where the residual RL and skill synthesize. Let me explain what does that mean. So after the imitation learning based policy, we get a generalist. But we can enhance its ability for different embodiment. So through the residual RL pipeline, built on top of Isaac Lab using the powerful visual RL capability of Isaac Lab, we can build the specialist or expert for each of the embodiment or each category of the embodiment. For example, as we can see here, it's including the quadruped and also humanoid and also wheeled robots as well. And then after that, you get the specialist experts for each category of the embodiment. And of course, you can also bring your favorite robots into this residual RL fine-tuning pipeline as well. And then after that, we have the specialists all sitting together, ready to empower more powerful things. So then we do the cross-embodiment distillation. So after that, we got a more powerful generalist policy. And here, we open source the code, also the models, the data set, and so that you can try it. And also, you can bring your robots to give it, see how it looks. And so here are some examples of cross-embodiment across different humanoids and also quadruped in different environments like offices, warehouses, different type of warehouses as well. And again, you can also bring your digital cousin or digital twin of the deployment environment you want to use. Let's see if you want to deploy that in the outdoor environment. You can also do that. You bring those digital twins to the training pipeline we just shared, and then you get a better fine-tuned model for it. And also, we deploy this into Mega. This was also showing in yesterday's keynote. So the agility digit we are seeing here is powered by the campus models we just saw. And also, the Mega is a really powerful platform where you can testing multiple embodiments, different type of robot brains and different type of like the robots in different environment in the same platform. And also, the other nice thing is like for all the models we just shared, we never used any real data, but we achieved the zero-shot sim-to-real transfer for the mobility. And as you can see, this is another embodiment. And so next, after the mobility, so for different embodiment, we know that people will prefer different type of controller for it. And for humanoid, we also provide you a workflow building in Isaac Lab that you can train the powerful neural whole body controller for humanoid. So why does that matter for whole body controller for humanoid? So for controller, actually it runs on hundreds or even thousands of hertz. And for that, it needs to be lightweight, and it also needs to be really capable of doing any upper body and lower body actions. And so again, from Gear, there is really nice research called Hover, and it enables the robots, the humanoid robots, to take the different control modes and then generate action accordingly. What does that mean? So you can have the Apple Vision Pro to directly control the robots, or you can have an autonomous policy that maybe have, for example, the upper body related actions. You can also have the mobility policy, which gives you the root velocity command. And so with the hover policy, you can use all those control input modes to control your humanoid. So next, let me share how we do that. So firstly, the journey started with data again. So you can use the large-scale motion data set. Actually, those motion data set can directly coming from like videos, human videos. So in theory, any dance you want to do, you can put those actions into the pipeline, and you can teach the robots to perform those dances. And then another step to retargeting those motions into the motions that can be done in the specific humanoid, because we know some humanoid is super capable. It can do a lot of complex maneuvers, while some of them might not be able to do all those fancy movements our human is doing. Okay, so with that, you got the feasible trajectories that we can learn. And with those trajectories, and then we go through the steps in the Isaac Lab for the training. So firstly, we train the RL policy with all the privileged information, meaning that you can get all the, for example, the drawn states that it's very hard to get in the real world. And then you got a really powerful policy there. And then after that, we do the imitation learning to do the student distillation. So there, you actually use the input that can directly get from the different control modes that I just mentioned. And there, we also do the random masking so that you actually get the capability of using the different control modes to control it. And another nice thing is that we open source the hover implementation in the Isaac Lab, and it not only doing the hover, but in the same repo, you also got a specialist Omni H2O innate as well. And also we do the same validation and same to real. Again, all open sourced. And so from here, you can see that the robots are trained in the virtual environment with all kinds of different motions. And on the left, you can see the terrain is quite rough, and we can even put the stairs on top of it. And on the right, it's also showing that tons of humanoids is doing the training together. So using the Isaac lab, you actually get super accelerated physics. So 10,000x faster. So to put that number into perspective, what does that mean? So that means the robots can undergoing the very intense training for 1 year in just less than 1 hour of clock time in single GPU. Okay, and see that the robots is also saying hi in the digital world and also real world to you. With that, I will hand the mic to Leela to share with you how do we define the real robot in the edge computer with Thor. Thank you all.
Thanks, Jan. So it's been a great session so far. You heard from Jim and UK about kind of the latest on N1, and then you heard from Jan a little bit about kind of our workflows, as well as using the first 2 computers for training and adapting. Now I'll be talking to you a little bit about our 3rd computer, Thor. And before I go into more details on that, I wanted to talk to you a little bit about what we've been seeing. So we've been developing Jetson and Edge AI for some time now, a little over 10 years. And with that, we've seen in robotics a lot of commonalities. So historically, a lot of the applications were specialists, kind of like what UK and Jim were talking about, where they were doing one single fixed function, whether they were picking and placing or focusing on perception in an AMR in a factory, or in a last mile delivery, having to figure out navigation. Now we're seeing, over the past 12 to 18 months, with the rise of generative AI, there's also been this rise of humanoid robotics. And so that's something that we're considering and developing with our 3rd computer. And so with that, some of the things that we've thought about when developing our computer are, what does it actually take to build a humanoid? What are the different components of it? And so we found that across multiple different humanoids, there's this common architecture where there are 4 different layers. At the base, there are a lot of different sensors. So whether that be cameras or IMUs, actuators to be able to control the robot, audio and microphones to be able to communicate with the robot and tell it something to do, cameras for it to be able to perceive the world around it, and then position sensors for it to be able to encode its actions and react based on that. That's really at the base, along with the compute platform. The next layers are really related to those 2 brains that you were hearing about earlier, where there's one brain really focusing on the real-time control framework. And the latency on that is much more critical. You don't want your humanoid to fall over. And so with that, whether that be the velocity controllers, the position controllers, or the torque controllers, we found that they often need somewhere between 100 to 1 kilohertz. And then for perception and planning, as well as high-level reasoning, it's a mixed criticality use case. So that means those don't have as tight of a control loop, whether that be for the object recognition or the grasping and motion that's being done, or the locomotion, as well as scene understanding. That's anywhere from about 1 to 5 hertz or 30 hertz. And so these are all things that we've thought about in terms of how are our customers going to be deploying some of these applications on our compute platforms. And with that, now I'm going to share with you more about NVIDIA Thor. It's really designed to be the ultimate platform for humanoid robotics. It's built for safe and secure next-generation robots that are being accelerated by bringing transformer models to the edge and running on these runtime computers. With Thor, there are really 4 key pillars. The first is being a supercomputer for humanoids. So we found that customers want to be able to deploy large transformer models at the edge and on this runtime computer. And so last year, Jensen announced that Thor had 800 FP8 T-flops. We're excited to showcase that now we've increased that to 2 petaflops of FP4 performance. This will enable you to be able to accelerate a lot of large transformer models and be able to take advantage of all of what you've been hearing about today by being able to run Groot N1 and all of the development that's also being done in sim and lab, and then to be able to deploy it on this supercomputer. The next that we found is that high-speed sensor processing is essential. As we were just covering, a lot of humanoids and other applications are trying to bring in lots of different types of sensors and large amounts of data. It really comes down to a balance between compute, I/O, and memory. And so with that, our platform will support up to 425 gig of Ethernet. This is a 10x I/O improvement compared to our previous generation. Not only are we increasing the I/O, we're also introducing new architectures to help streamline your development. As developers, we want to make it easier for you to be able to connect sensors to our compute platforms and get them up and running easily. And that's where we've developed something called Holoscan Sensor Bridge that takes any kind of sensor data and brings it into our platform via Ethernet. This is really essential for real-time, low-latency applications. In the Thor architecture, there's a new offload engine that enables really low latency between the sensor entering the system and getting to GPU memory. The next piece that we think about is safety. We think about safety in kind of 3 different pillars. There is the platform level safety. So in the SoC itself, there is a functional safety island. It's an isolated island with a set of 4 lockstep R52s. And this will enable you to be able to run and gather data around errors that may be occurring. There are a number of IOs that are also on this portion of the architecture to make sure that it's secure the data that's going back and forth between an MCU and the solution. The next is end-to-end safety. That's where you have sensors in your system and you have your compute. And you want to make sure that link between the sensor and the compute is safe. And so in Holoscan Sensor Bridge, we built it for up to SIL 2 level safety. The third is AI-based safety. With AI-based safety, we think about it in 2 different ways. The first is the humanoid itself has sensors on the humanoid, and it will enable it to perceive the world around it. We think of that as kind of, it can perceive within a bubble. Now, if a humanoid is walking down an aisle of a factory, like some of the images that you were seeing earlier, and it can't see on the other side of the wall, the factory may have other sensors that would be able to communicate and send information to the humanoid to tell it, oh, someone's coming around the corner. And that's something that we called outside-in based safety. The next pillar is security. We think about security also in 3 different pillars. The first is platform level security. This is things that we've done similar to our previous generations, like secure boot, secure root of trust, memory encryption. The next is we're seeing that a lot of our developers are creating custom IPs, and they want to make sure that that is secure. And so that's where we're adding model level encryption as well. And then the third is edge to cloud security. There are some things that are going to be running on the device itself, and then some that are running in the cloud. And you want to make sure that the link between them is not tamperable. And so we're adding things like firmware-based TPMs to enable that. And so with that, introducing NVIDIA Jetson Thor. So how are we able to get to the jump in performance of 2 FP4 petaflops? It's because there's a new GPU architecture that's based on Blackwell. There are 2 key things that I want to highlight about this architecture. The first is there's this new transformer engine within the architecture that enables native support for FP4 and FP8. And these are precisions that are really essential for a lot of large transformer models. The second is we're supporting something called multi-instance GPU. We support this on our other GPU platforms, but this is the first time that we're supporting it in our embedded edge platforms. This is really critical for mixed criticality use cases. We were talking earlier about how some portions of the applications have really low latency, and some aren't as latency critical. With MIG, you can basically take a single GPU and segment it into 2 different GPUs and run the applications in parallel. The next key component, so this module that you can see here, it not only contains a GPU, it also contains a CPU, accelerators, memory, and the power architecture, all into this small 100 by 87 millimeter form factor. And so with that, we found that for a lot of applications, especially with humanoids, real-time control is really essential. And so we've also enhanced the CPU with a Jetson AGX Thor with 14 Poseidon AE ARM cores. This is 2.6x the performance of the previous generation. Transformer models, memory capacity, as well as bandwidth is also essential. And so we've doubled the capacity to 128 gigabytes and increased the bandwidth to 273. We talked about also the jump in I/O, a 10x I/O improvement compared to the previous generation. Availability of Thor will be in June of this year. So let's jump into a little bit more about the SoC architecture. In the middle, you can see the GPU. It's divided into 3 different clusters. We talked a little bit about the AI performance. There's not only a jump in AI performance, there's also an increase in the CUDA performance, around 8 FP32T flops. With MIG, you can basically isolate it into 1/3 and 2/3, so a single GPC and 2 GPCs. On the CPU side of things, that's where we have those Poseidon AE ARM cores that support architecture V9. There's a platform security controller to enable those security features, as well as a functional safety island for up to SIL 2 level safety. There's a shared memory architecture, which makes it really easy for the pre-processing and post-processing that may occur in your sensor processing pipeline to develop. And then we have multiple different accelerators for offloading portions of your applications. So whether that be our programmable vision accelerator for offloading CV algorithms or our optical flow accelerator. We have something called the Vision Programming Interface, which is the software which you can use to develop with the PVA and OFA, and you actually don't even need to wait for Thor. You can start some of that development now with our previous generation Orin. We also include a number of other accelerators, including an ISP for image processing, as well as a video encode and decode. Compared to our previous generation Orin, we've doubled the amount of encode and decode. So now you have an understanding of what is the compute capabilities both from a GPU, CPU, accelerators perspective. Now it comes down to I/O and memory. From an I/O perspective, we have the 425 gig of Ethernet. We have up to 12 lanes of PCIe Gen 5 and up to 16 lanes of CSI. We also support a number of sensor I/O. And at the bottom, you can see we're now enabling that higher bandwidth with support for LPDDR5X. So moving into a little bit more details around the platform software. The software that we've focused on so far is accelerating your development and at the application layer. And then underneath that, we have this base level software that includes some of these frameworks, libraries, SDKs. And in terms of the kernel and Ubuntu versions, you can see up on the screen. So we'll support up to kernel 6.8, and Ubuntu will be 20.04. Multi-instance GPU support will also be coming with our Jetpack 7, which is going to enable the new Thor platform. The other thing that's really essential for humanoid applications is real-time computing. And that's where we have support for preempt RT patches that you can enable for some of that real-time computing requirements. Next, jumping into our developer kit. So our goal is to really accelerate your time to market and your development with these platforms. And so that's why we create a developer kit that includes a carrier board, the module, a thermal and cooling solution. And with that, the number of I/O and the I/O that we looked at kind of took into account the requirements that we were seeing for humanoids. For example, we wanted to make the wiring simpler for if you're going to connect this developer kit to an existing robot. So we placed all of the I/O on one side. in terms of the I/O that we support as well, we took into account some of the requirements of multiple different sensor types. So we've added native support for the 25 gig via QSFP slot. There's support for multiple displays, as well as support for multiple USBs. There's also a microfit for extending the power. There are various automation and CAN headers for other sensors. And then with our previous generation, we heard some feedback that customers wanted more storage. And so that's why the developer kit will come with an integrated 1 terabyte NVMe of storage. There's also be a second slot for the Wi-Fi module. The developer kit is really designed to accelerate your development. Another piece that we are designing to accelerate your development is Holoscan Sensor Bridge. This is our sensor to Ethernet streaming platform. As you saw, the dev kit has 425 gig of Ethernet. And so with that, we found that across a lot of humanoid applications, there are multiple different types of sensors. And today, the way that you have to develop them is you have to get the drivers working for each individual sensor. They may have different interfaces. And both from a hardware and software development perspective, that can sometimes be time consuming. And so we wanted to make it easier for you to use. So Sensor Bridge brings in any kind of sensor, whether it be a camera sensor, IMU, audio, motors, encoder, and we've developed a custom UDP protocol that converts that data into Ethernet. And on the Thor architecture, there's the offload engine that will bring the data directly into GPU memory. This enables the ultra-low latency that's essential for some of those control frameworks. Not only is it easy to use and low latency, it's also scalable. So we found that some customers may want to change their sensors over time. Today, the way that you do that is you may have to re-architect your system. Our goal is to make it modular in nature so that that way you can change your sensor without having to re-architect your system. And then the last thing is safety and security, which we found is essential for a lot of these applications. Sensor Bridge is qualified for up to SIL 2 level safety. And then lastly, in terms of jump-starting your development, we found that for customers, integrating can sometimes take additional time. And so we don't want you to have to wait for full integration to start development with our Thor platform. And so we've designed the developer kit both from an I/O and wiring perspective so that you could easily tether it up to an existing system. You can also put Sensor Bridge in the middle to connect new sensors. And you can easily start your development now. And with that, to summarize what we've shared with you today, first, we talked about the latest with our Groot N1 model. Then we went into some details about our 3 computers and how you can leverage our different workflows for accelerating your development. And then finally, I closed with a little bit about our 3rd computer, the runtime computer. And with that, I think it's time for Q&A.
If you have a question, just raise your hand, and we'll give you a mic. One second.
Hey, great presentation. Quick question on training. Is there a preference for real data versus simulated data, or do you treat it as equal?
So real data will be the highest quality, but like the volume will be smaller, right? So so we have to combine both. So, but what we found is only simulation alone is not enough because you do need some real-world data because they are collected from real-world sensors with real-world motor noise, right? So if you can combine the simulation data with only 1% of real data, it will dramatically increase the performance than just only training in simulation data alone.
Maybe you can tell them about the results you achieved with synthetic data in your model training.
Yeah. So we have more detailed results in the white paper, but you can see that so we do update training sim versus a combined training. Yeah.
Hi, thank you all so much. You guys are an amazing team and very clear with your presentation. So I'm just wondering, it's so amazing you guys are making it open source because it's the collaboration and the quickness that's going to get humanity there, right? And ultimately to help in various ways from specialized robots to flexibility and adaptability. So my question is, with the moonshot, is NVIDIA's the vision to be able to, this is what I'm saying, it's like now you can white label certain platforms where now you can also customize your robot at home, like how you pick various variables on a car, select it, it gets customized at a factory and delivered to your home. Because even though everybody has various usage needs for, let's say, a humanoid robot, you know, even a person that has dementia, they have a different issue, or comorbidity, or different health issues, right? So that's why it's so important to have the simulation training to do that. So I was just curious about your thoughts.
Yeah, so the question is about kind of different use cases for the model, right? And also you mentioned a little bit on kind of different embodiments, perhaps. So I think it's really important that the robot foundation model is general purpose. So someday we'll be able to prompt it with any language that the hardware is capable of supporting, and it's able to go ahead and do the things, right? In hospitals, right? Like caring for the elderly, at homes, right? Doing all the chores, right? Everything, right? I always dream of having just a cooking robot, a cleaning robot, and perhaps more than one. So, right, like I can feel like I live like king, right? So I really want to see that future. It's not there yet, but I hope it's around the corner. And also in factories, right? There are many tasks that are actually very dangerous for humans, right? Like the workers, like they really risk their health to do many of those tasks, right? And then those should be automated. So I think we are taking major steps, but also first steps towards this goal. And there was a great saying, I think it was from maybe DeepMind CEO Demis. He said that he wanted to solve AI first and then use AI to solve everything else. And so if we believe that's true, then AI becomes the last technical problem that we as a developer community needs to solve. And I will take it one step further. I would say robotics is the last standing challenge of AI. So apparently, it's actually easier to do reasoning, to do language, to do white-collar work than to actually do physical work. That's what's known as the Moravec's paradox. The things that we humans find easy are actually really hard for machines, and the things that we find to be hard are easier for the machines. So I think that's why robotics will be the last grand challenge. And we're not there yet, but I think with Groot, with Isaac, all of these product and research threads, that will get there sooner.
Hi, thank you for a wonderful talk. I have one question regarding the Groot architecture. Is researchers nowadays in the body AI are seeking different architecture. We're trying to certify which one of them are the best. There are approaches that only trains in VLA, only system 2. And there are other approaches that only scaling up diffusion transformer, like system 1. So do you believe that the architecture, this kind of architecture of Groot, is like the final answer or the right path for a scalable, generable embodied AI? And what do you think of its advantages? Thank you.
I absolutely love this question. So first, I would say definitely no. We never have final answer. I think AI robotics will keep evolving. We'll never have final answer. And maybe someday we'll even see transformer may not be the main architecture anymore, right? So getting back to your question a bit more on the technical side, there are many different approaches right now for vision language action model, right? Groot N1 is one type of vision language action model. And there are models that take a purely discrete approach. Basically, you discretize the actions. You turn all these continuous motor values into integers. And then transformers love integers, right? If you turn things into integers, you can use a single sequence model to predict everything. So that's one approach. And the other approach is this kind of hybrid system 1 and system 2 approach, like what Groot N1 took. So it uses like a diffusion model to render the actions, because diffusion is better at floating numbers. I would say both approaches have their own pros and cons. And then the jury is still out there. But I think there are certain properties, certain capabilities that we still hope to see to be much stronger, maybe in the next iteration of this technology, right? Like one is much stronger computer vision, right? Like make it extremely robust under all kinds of different settings. And the other is reasoning. How do we add, right, like very complicated chain of thought and reasoning to it? Like recently we have seen, right, OpenAI, like O1, DeepSeek R1, like all doing these chain of thought, very long reasoning, right? This agentic thought trace. And we also hope to add those to robots as well, so they can break down a task, a physical task, in much more granular steps. And what is a better architecture for planning? I think the jury is still out there. But we just know that we need to solve planning. We know that we need to solve computer vision. We know that we need to have smoother, right, continuous output. And whichever architecture delivers these capabilities better, we'll adopt, right? I think as researchers, we cannot be picky, right? We cannot afford to be picky. We cannot afford to be opinionated. It's really important to see some breakthrough and quickly adopt it. And I think NVIDIA moves at the speed of startup.
Mm-hmm. Yeah, and maybe I just add one more bit is like, why not wait for computer vision researchers or like a language model researchers to solve computer vision or reasoning, and we can easily take it, right? So, and all these techniques and capability need to be deeply integrated, because like a robotic does vision in such a interactive, real-time situated settings, and so as reasoning, right? So right now, most of the language model does reasoning with a vehicle thought of like text tokens or language, right? So, but robotic reasoning needs to be happening in the here and now and grounded in the sensor motor space. How do you actually do some kind of latent reasoning that connect with a sensor motor stream? So that's interesting research question that we are also actively exploring.
Hi, sorry, very loud. Fantastic presentation, tone, delivery, content, I loved it, thank you so much. And one question I had was, one of the things that was said during the talk was pointing out how incredibly close to real life data the simulated data looked, and I agree, it was incredible. So I focused very hard to try to figure out how I can tell them apart, and one of the things I noticed was the shadows and some of the lighting conditions. So my question is, and I know that you're also working on more photorealistic data, but my question is, when you were playing around with your model and its performance, did you notice any differences when you're performing tasks under very varied lighting conditions, and how robust is the model to like shadows and yeah, just generally that.
Yeah, I think this is a great question. I mean, like, so like that kind of like a visual robustness can be largely improved by just randomizing the lighting conditions, and during the synthetic data generation process, it's very easy to change the lighting or kind of like rearrange the things so that so you create a little bit variety of conditions and to augment the data set for that level of generalization. Definitely, so there's also a limitation to it, right? So I think that part of it is like coming from the VR backbone, that I think if we have a much better VLMs that can handle better object recognition and the spatial understanding, that potentially can improve the robustness and generalization of the model further. I think like regarding your question about the synthetic, I think we have shown good visual realism. Like, so for that part, I don't think that's like the current critical or pinpoints, like, so, but the physics part is actually a bigger open problem to solve, right? So especially if we are dealing with like a more complex physical phenomena like liquid and smoke and other things, right? So and that sort of things like the traditional simulator has struggled to deal with, but now we see with Cosmos, with all the newer models, like potentially they can support like those more complex physical phenomena so better than the kind of classical like physics solvers. Yeah.
Yukin had mentioned that simulations haven't really taken off. Can you elaborate more about that?
Simulation? Yeah, I mean, that's really kind of like NVIDIA's bread and butter, right? So I mean, kind of before we are an AI company or a graphics company, right? So we really do like decades of our work on kind of physical simulation, graphics rendering. We know really well how to generate nice pictures, pixel level rendering, and also we know really well how to do good physics. And historically, those tools has been developed mainly for entertainment or kind of gaming purposes. But we realized so these are actually also essential tools that can benefit for robotics. And I think usually this is the core of our strategy. And over the years, we see that as the robotics industry gets bigger, there's more players in the game, and so there's more interest in leveraging physical simulations, and there's a lot more critical mass in recent years that really drive the development of all those tools and infrastructures, right? So that's why we see that so simulation has becoming playing a more salient role in the robotics development stack, because there's just better tools available, like larger scale assets, and including more better ways to run kind of scalable physics with GPU acceleration.
Hey, thank you for the presentation. My question is more on the next bottleneck. Considering you have already showed great progress in data side by leveraging the simulation, what do you think is the next bottleneck? Is it the hardware or other more compute or anything else?
Yeah, so I wouldn't say it's a bottleneck, but it's more of an interesting kind of next challenge that we want to overcome. And the challenge is finding what is the scaling law for robotics. So for Groot N1, we just started to answer this question, right? We generated this data set and then we trained this model, but we have not kind of scaled it to even more orders of magnitude, and then study, right, how scaling on real data, how scaling on simulation data, and how scaling on these kind of neural trajectories, neural generated data help the final performance. So I think Groot N1 laid out the foundation to answer these questions. And we just need to be more systematic in exploring these data strategies and really kind of quantify these things. I think the pivotal moment in LLM was like GPT-3, right? Showcasing, and Chinchilla from DeepMind, showcasing the scaling law. So people have seen that when you throw a lot of parameters at a model, throw a lot of data at it, it's going to achieve great things. But people don't really know, right? Like how these things scale with more compute, scale with more data, so you can basically predict, right, what performance you're going to buy with your money, which I believe is probably a very important question to a lot of people in industry. So we are setting out to answer that.
Thank you very much, Jim. Actually, my question is very similar to that, and you answered part of that about scaling law. So the next part is, do you have a vision around what this ChatGPT moment is like for robotics? What does it look like?
That's a great question. I think it's going to look like open-ended instruction following. So one of the reasons that Yuke also mentioned that we work on humanoid robot is because this is the most general form factor, right? In principle, a capable enough humanoid hardware can do everything that an able-bodied human can do. And that basically has no ceiling, right? Just think of all the things that we do, right? Like from athletes, right, to workers, to everybody. Think about all the things we can do. And then a humanoid robot is in principle capable of that. So I think the limitation is still on the AI side. The hardware will definitely get much better, and we have already seen extremely capable hardware, and it will get much better in the next couple of years. And I think AI intelligence is the part that's a bit trailing behind. So I would say the ChatGPT moment is when we get good enough hardware that can support everything, and then we have just open-ended language prompting in any scenarios, right? Household, right, like worker in factories, hospitals, any scenarios, you prompt it, and then the robot can do anything that a reasonable, normal human can do. That would be the ChatGPT moment to me.
Hey, Jim. I agree with your assessment of the ChatGPT moment. My name is Chris, and I lead electrical design for Optimus at Tesla. And,
amazing.
And,
state-of-the-art hardware.
Yeah, we're very appreciative of the work that you've done for industry as a whole. Coming from the hardware side, I saw a few specs on Thor in particular that I was interested in asking about, particularly like power consumption. So it said like it was 120 watts. Is that continuous power consumption, or is that peak power consumption?
That's max power. That's max power. That's so max you can, power. Okay. Yeah, you can design your own workload depending on kind of what you're running. To run it at lower power modes, it's kind of dependent on your use case.
Gotcha. And the CAN interface, is that CAN FD or is that just standard CAN?
Standard CAN.
Okay, got it. Cool. And then one final question I had regarding voltage for that power interface. Is that like what power supply input voltage is it that it accepts on Thor?
We'll have more details on the voltage architecture closer to availability. We'll have some detailed documentation around the June timeline.
Awesome, that sounds great. And I look forward to reading those white papers, by the way. Coming from the hardware side, I don't really see a lot of that software like abstracted layer, so it's really exciting to see what you all have been up to. Thank you.
Awesome, thanks.
Hi, my name is Neil. Very interesting discussion, really like it. So what we saw in the demo, we saw like the human and robot is like moving very slow, like it's very, you know, you're afraid to touch him so he won't break. So when do you think you can reach to a level that it can be like you can feel a real human, not afraid to touch him or give him the flower, and hopefully will give him the glass, something like that.
Okay, yeah. If you see the, did I show the dancing and jumping video, right? So the robot actually can run very fast if you run max torque, but maybe you don't want to do that like right next to you, right? So and there's a safety reason to it that we run at a slow speed, and just like we still want like a more like a safe and a more compliant robot, especially like for humanoid, we're not gonna like build them in cages, right? So they stop making sense as a humanoid. So we are going to deploy that in the human world. That means that like, so they're going to share a physical workspace with a human, right? So, and then all the safety considerations, like, so in the kind of human robot interaction, coexist in the same space that come into, I think this is, we see like, so Jim mentioned, like, so definitely a lot of the core challenges are fundamental AI challenge, but also I do believe that like, so this is not just an AI problem alone, right? So we need to do the hardware software co-design to explore a bigger solution space, and the hardware will continue to evolve. Like, so we are working closely with the industry partners to adopt like a better like hardware advancements as well. But I think for that, like, so definitely the robots are capable of kind of running high speed, right? So, but if they fall to humans, it's gonna giant human nutcracker, right? So it's scary, right? It's like 100 pounds, like a robot falling onto you. So you don't want to do that. So yeah, so and that's why that we're kind of actually artificially limiting the speed of the robots just to be safe for now. But definitely we want to see a safer, softer, maybe more compliant robots, so we can safely deploy and to be able to perform more agile behaviors. Yeah.
Thank you for the great presentation. So 2 questions related. Number 1 is, I noticed you guys are taking a lot of learning from the video vision. So that's, but you didn't talk too much about the actually when you use the hand control to carry, how you actually learning the sensing, like the torque, the sensor, that part of the learning, do you actually capture that into your overall learning inference as well? So the second question is, I noticed that you have like a very high speed, like 20 gig Ethernet over there. So the thing is, do you actually, everything is controlled and interpreted by your supercomputer at the brain, or you're also trying to build the intelligence into in your hand? So your hand has some sort of intelligence as well to respond to very fast moving world. Mm-hmm. Is that, so basically you have like the central control, or it's kind of like a distributed by a different hierarchy. Thank you.
I mean, if you look at like the human neural cortex, like the control system is highly decentralized. It's not that everything comes like from the big brain, right? So I think that's kind of like also the architecture designs of like, so for the policy of the Groot N1 model, it offers some kind of task-based commands, and just to show the high-level motion, where's the target locations the hand should supposed to be moved to, but how to exactly realize the motion or reach the kind of like target configuration of the robot that relies on underlying low-level controllers, right? So that's running at much higher frequency because like the robot needs to stay balanced while kind of interacting with the world. Typically, it's some kind of a whole body controller that runs like 1,000 hertz. So that's still not part of the foundation model yet because like you need that kind of high-speed inference in order to run that kind of like a fast control loop. But there are some interesting questions like, so what's the right interface, right, to connect the foundation model with the lower level control modules?
Hello, thank you very much. Great talk. My question is about FP4 number format. What exactly kind of FP4 is supported by hardware? Is it MX FP4 or NVIDIA FP4 or just FP4? Thank you.
The hardware is natively supports FP4 in that transformer engine architecture. And so it natively supports both FP4 as well as FP8 and FP16.
Excuse me, is it NVIDIA FP4 or MX FP4? Is it block number format or just number format?
You can support BFloat as well if you need to. Underlying is NVIDIA FP4.
Yeah, and that's our last question here.
So I'm Alex of ARM, so thank you very much for using ARM CPUs in the product. Great presentation. Question, maybe I missed that. How do you measure success? Is it like pass at 20 or what's the metric that you are optimizing for?
Yeah, so we have a wide variety of benchmarks in Groot N1. So we have the real world benchmarks for sure, and also the simulation benchmarks. The simulation benchmarks, we hope it can provide the community with some reproducibility, because yeah, like not everyone can set up the robots in the way we can. So it's much easier for people to try in the simulation. And then we have these kind of systematic settings. So let's say in the kitchen setting, right, we place objects in particular locations, and they're randomized. Also, there are different kind of object categories, container categories that we randomize over, and then we record success rate systematically. And in simulation, it's just much easier. You can roll out maybe 200 episodes and then measure success. So we have found that in many scenarios, Groot N1 is able to outperform like prior state of the art by something like plus 30% on the success rate. For certain tasks that are like just grasp and then pick and place, there are certain times that it can get very high success rate, like over 80%, over 80 or 90%. Yeah, and I think N1 is going to be like it will be a continuous project. We'll keep adding more data to it as we're studying the scaling law, and we hope that the next version, and we'll keep open sourcing it, next version will be even better. Thanks.